Okay, we are recording. First time I do this, so it's new to me, like for all of you. Well, hello everyone, and thanks you for joining us today. It's a real pleasure to welcome you all to this talk, and an even greater pleasure to introduce you to the speaker today, Professor Hannes Leitgieb. Professor Leitgeb is one of the leading figures in contemporary philosophy, but particularly in areas where logic, mathematics, and epistemology intersect. He holds the chair of logic and philosophy of science at the University of Munich, and he is also, as you may well know, a founding member of the Munich Center for Mathematical Philosophy. With doctorates in both mathematics and philosophy, Professor Leitgeb brings a rare and powerful combination of technical expertise and philosophical insight. His work covers a wide range of topics, including formal theories of truth, belief revision, logic, and the philosophical foundations of mathematics and science. He has published extensively, received numerous awards and fellowships, and contributed in important ways to shaping how we think about the relationship between logic, language, and knowledge. He is also, and this will be fun to know for a lot of you guys, he's also the author of the entry on rule of Carnap in the SEP. Yeah. We are, and most recently, Professor Leitgeb was awarded the Leibniz Prize for the most important and prestigious work there, I think. So that's an outstanding work for Professor. We're especially grateful for Professor Leitgeb to accept our invitation to speak here as part of the activities of ACHEPA, the Chilean Association of Philosophy, Analytic Philosophy Students. His presence is a true honor for us, and we deeply appreciate his generosity and taking the time to share his work with our community. Today, he will be speaking to us about mathematical philosophy. All of you work on that area, or at least have read something about it. Well, I say no more. We're very fortunate to have you with us. Please join me in your minds, in your hearts, and maybe in the chat, in giving a warm welcome to Professor Hannes Leitgieb.
Thanks so much, Martin. Thanks a lot. I hope you can all hear me fine and see my slides fine when I change them. This all works fine, yeah?
Yeah, it's all good, Professor.
That's great. Thanks. So thanks so much for having me. It's a great pleasure and honor. And thanks, Martin, for setting that up. So Martin asked me to give a talk on mathematical philosophy. And since this is very close to my heart, it's of course a pleasure to do so. As Martin mentioned, I first got a PhD in mathematics, and then afterwards I got a PhD in philosophy. And I always thought that sort of my mathematical background served me quite well in my philosophical work. And I'm not the only one to think that. So let me start with a little quote here by Bertrand Russell, who says in this little treatise on how to become a philosopher, "Whoever wishes to become a philosopher will do well to acquire a considerable knowledge of mathematics. In the course of this study, he will get to know what sorts of truths can be discovered by mere thinking without the help of observation. He will also acquire familiarity with exact reasoning and with the sort of mistakes to which even very expert reasoners are prone." And that's exactly my attitude towards the usage of mathematics in philosophy too. And the good news is you don't have to get a degree in mathematics before, doing mathematical philosophy in my sense of the term. But it's sufficient to get enough mathematics on board when and where it is useful in philosophy. And if it's not useful for a certain topic, then that's also fine, okay? So let me start by explaining what I mean by mathematical philosophy, or as some colleagues of mine would also sometimes say, formal philosophy. As far as I'm concerned, it's the same thing. What we mean by that is philosophy done with the help of mathematical methods, which includes for us logical methods. Okay, so it's really the application of logical and mathematical methods to philosophical problems and questions, including, very, very, very traditional philosophical problems and questions. So the idea is not to change sort of the subject matter of philosophy, it's what it is, but rather to use logical and mathematical methods to address our traditional philosophical problems and questions in a better way. That's the task That's the aim. Okay. So in particular, the idea is not to reduce philosophy to mathematics or so. That would be absurd. You can't, right? It's like physics, right? Physicists use mathematical methods all the time, but of course they do not thereby reduce physics to mathematics, right? That wouldn't work. And it doesn't work for mathematical philosophy either. So mathematical philosophy is still philosophy, but it's only helped by mathematics. That's all. So when I say mathematical philosophy, I don't mean philosophy of mathematics. Okay, so mathematical philosophy could be, you know, epistemology, or it could be philosophy of science, or metaphysics, or ethics, and whatnot. Pretty much everything in philosophy, in principle, can be helped by mathematical methods. Okay, philosophy of mathematics, where we reflect on mathematics philosophically, can also be helped by mathematical methods, and in that sense can also be mathematical philosophy. Okay, but you can also do philosophy of mathematics in an informal manner, and sometimes, you know, that's the way to do it, and then that's also fine. Okay, in any case, mathematical philosophy is not the same as philosophy of mathematics. Okay, and finally, as I said, some people would rather say formal philosophy, but it's the same thing. So for example, there is an annual formal epistemology workshop, which I can recommend very much. There is an event series called the Formal Ethics Week, okay, which I also can recommend very much. That's all part of mathematical philosophy. Now, there have always been mathematical philosophers in that sense. Leibniz would be one of them, but you can go back further. If you go to, you know, ancient philosophy, ancient Greek philosophy, if you look at Aristotle on logic, right, his syllogistic reasoning, that's for me a part already of mathematical philosophy. Okay, but in the past, some philosophers have also denied that mathematical methods could play a substantive role in philosophy. You don't hear that these days very often anymore. I mean, I don't hear it at all, to be honest. Okay, but back in the past, philosophers sometimes did think that you couldn't do philosophy mathematically. A paradigm case instance would be Immanuel Kant in the Critique of Pure Reason. Okay, I'm based in Germany, so in my contract I have it that at least once in my talk I need to cite Kant. Okay, so that's why I bring it up here, right? So I've just fulfilled that duty. This was a joke. Okay, so when you read Kant's Critique of Pure Reason, you find this part called the Transcendental Doctrine of Method, where he argues that philosophy cannot be developed according to the definitions, axioms, proof scheme that the mathematicians like. And the reason that he puts forward is that for Kant, mathematics is something that is concerned with pure intuitions, Anschauung, right? Like in geometrical intuition. Whereas philosophy for Kant deals with pure concepts, and so, you know, by that difference, you couldn't use mathematical methods in philosophy because philosophy lacks the geometrical, say, intuition. Okay, and from his point of view, this made quite good sense because he thought of mathematics very much to be captured by Euclidean geometry. And if you think of Euclidean geometry, if you read Euclid, right, then you can see when Euclid defines geometric concepts, right, what a circle is, or a triangle, or a parallel, or something, then he always presents a construction method, right, for circles, triangles, parallels, and so on. And these construction methods are to be applied in the Euclidean plane, of which we do have, indeed, some kind of geometrical intuition, right? And that is what Kant picked up. And then geometrical axioms would be justified by intuitions. And if you again look at Euclid when he gives geometrical proofs of geometrical theorems, then in the proof, he also makes use of geometrical constructions in the Euclidean plane. And of these constructions, we again need to have intuition. Okay, so from Kant's point of view, his argument in the Transcendental Doctrine of Method made quite good sense. But, and that's my point, it doesn't make good sense anymore from our modern point of view, because in the meantime, right, since, you know, the 19th century, but, you know, very much then in the 20th century, mathematics has itself become purely conceptual or structural, if you like. Okay, so mathematicians themselves from the 19th century onwards have pushed back sort of the role of intuition in mathematics, and now mathematics is pretty much a purely conceptual affair, like probably philosophy is. Okay, so there is no difference anymore. And progress in logic, so that's the field where originally I come from, shows, in my view, that the space of concepts itself has an intricate and important mathematical structure that we can study mathematically, and that's also the reason why mathematical methods can pay off in philosophy. So Kant's argument doesn't go through. It's understandable that he put it forward from the modern point of view. It's not a sound argument. Okay. Now, the claims that I want to defend in my little talk today are the following ones. First, when philosophical theories are sufficiently precise, they can make use of mathematics. Okay, so you need to do something to make mathematics applicable to philosophy. You have to clarify, you have to precisify, you have to systematize. But once you've done that, you can use mathematics in philosophy. And more strongly, when philosophical theories get sufficiently complex, they may even be in need, they may require mathematics. Okay? And I hope to give an argument in favor of this thesis in terms of concrete examples. Especially, I'll give you 2 concrete case studies in sufficient detail, I hope. And then I'll give you a survey of methods of how we can use mathematics in philosophy. Okay, and I mean, this is not, a fictional talk. Okay, this is a report on what has been happening in the last couple of decades and actually even before. So it's something that's very much done now. It's done by many young, especially excellent philosophers. It's done on a worldwide level, right? Not just in Europe or North America. It's pretty much done everywhere. And, when useful, I can recommend the application of mathematical methods in philosophy very much for that reason. And at the end, I'll draw some general conclusions. Sometimes I will add some methodological reflections, and then I'll put them in red. So, now I'm commenting sort of on the meta level on what's happening, for example, in my case studies. Okay? So I hope you have an idea of what we will be doing now. And I will now turn to my first case study, which is to do with the acceptance or the acceptability of conditionals, right? So it's about if-then statements, if A then B. And the question that I'm asking is, under which conditions is a conditional if A then B acceptable to a rational and linguistically competent speaker, right? You could also put it in a normative manner. Under which conditions should you accept the conditional, right? You being a rational and competent speaker. Okay, that's my question. And I want to address that question ultimately with the help of logical and mathematical methods. So first, let me say this is not a cooked up question. It's not a question where already I built the mathematics sort of into the question, right? So far, there is no mathematics in the question at all. And you might wonder at this point what mathematics why mathematics should help you to address that question, okay? But it's an important question, right? So for example, it's an important question in the philosophy of language, okay? So my first case study is really in the philosophy of language. One reason why you should care about that question is because you might care about the pragmatic meaning of linguistic expressions. So what I mean by that, the pragmatic meaning of a linguistic expression X is something like the constraint that is imposed on you as a receiver when you hear that X gets asserted. Okay, so for example, I might assert, please open the window, okay? And then the constraint that I want to impose on you, the receiver, is, you should choose, if things go well, the action of opening the window. Okay, that would be pragmatic meaning of an imperative, right? In my case, I really don't want to open the window now because at nighttime, and now it's midnight here in Munich, it's still pretty cold here. So, was just a fictional example, okay? Now, you can ask the same question, what's the pragmatic meaning of a conditional of if A then B? And the idea, the typical answer is, the pragmatic meaning is, receiver, please be such that the conditional becomes acceptable to you. Change your state of mind so that if you take on board what I've told you, I've asserted if A then B, change your mind so that it becomes acceptable to you, okay? But in order then to say how you need to change your mind to do that, okay, to be a good interlocutor with me when you communicate with me, you better need to know what it means for you to accept a conditional, right? How does a conditional become acceptable to you? And that means you need to answer the question that I've asked before, okay? But obviously, right, conditionals are related to lots of topics in philosophy that we care about, dispositions, right, causality, natural laws, and so on and so forth. So conditionals are of central importance, right, and have been studied, as you might know, since, again, ancient times, right? Stoic philosophers very much were interested in conditionals. So it's been around for a long time. And the question is not a new one. It's an important one and a well-known one. Okay, so let me now turn to that question. Now, there is a famous footnote in a famous paper by Frank Ramsey, right, whom we know as a philosopher, but who's also cherished as an economist, for example, and as a mathematician, as a logician. And in that footnote, in his paper on general propositions and causality, he suggests a little test, and it's now called in the literature the Ramsey test for conditionals. Okay, and the idea is really, how do I judge whether I ought to accept the conditional? And what Ramsey suggests is the following. If two people are arguing if P will Q, that's the conditional, and are both in doubt as to P, so it's sort of an interesting case of a conditional, right? We don't know already that the antecedent holds, okay? What he suggests is these people are adding P, the antecedent of the conditional, hypothetically to their stock of knowledge, and then argue on that basis about Q, the consequent, the then part. Okay, and the idea is, right, if I want to know whether I accept the conditional, if P then Q, then I assume or suppose P hypothetically, and under that supposition, I check whether I accept Q. And if and only if I do so, then if I step out of my little thought experiment again, I'm accepting the conditional if P then Q. Okay, that's the idea. I'll return to that idea in a sec. You might see in this footnote by Ramsey, there's still no mathematical part, right? It's still just an idea of how to judge a conditional, well, by a sort of suppositional reasoning. That's the idea. And that's also why the Ramsey test is plausible, because it would really be surprising if the if-then in natural language had nothing to do with suppositional reasoning in the sense where I say, suppose P, is Q the case or not, right? So suppose and if obviously has a close connection, and that's what Ramsey uses when he formulates the Ramsey test. Okay. Now the Ramsey test has been around since the late 1920s, but in order to do something philosophically with it, it's necessary to become a bit more precise. Okay. So Ramsey uses these terms like knowledge, adding hypothetically to, that's the suppositional part, arguing on the basis of that supposition. But as long as we are not a bit more precise about these terms, it's hard to draw any conclusions, right? Whether the Ramsey test, for example, is a good test for the acceptability of conditionals or not. So we need to become a bit more precise. But before we do that, it's better to first look at some examples, because you can only abstract from something, right? You need to abstract from some examples, and then you can turn to the application of mathematics to make the Ramsey test more precise, okay? And that's exactly what people did. So, for example, famously, Ernest Adams did so when he looked at what's now called the Oswald pair of conditionals, okay? So Adams, a philosopher of language, looked at the conditional, if Oswald didn't kill Kennedy, someone else did. And he also looked at the conditional, if Oswald hadn't killed Kennedy, someone else would have. So the first one is formulated in the indicative mood, and the second one is formulated in the subjunctive mood, right? It's a counterfactual, okay? And what he observed was that we do seem to accept the first one, the indicative one, but we do not seem to accept the subjunctive one, the second one, okay? Because think about it, right? We all know what happened, Kennedy, Dallas, right? We're in the 1960s. Oswald shot Kennedy and, he died, okay? And now the conditional is, if Oswald didn't kill Kennedy, someone else did, and we would accept that, right? Because it might be actually, this was all, this wasn't true, right? Oswald was set up, but we all know still that Kennedy was shot, right? He's dead, right? He was killed in Dallas. So someone else then did it. So we accept the conditional. But if it's about the subjunctive mood, if Oswald hadn't killed Kennedy, someone else would have, we normally would not accept it, right? Because we think Oswald killed Kennedy, right? And so if Oswald hadn't killed Kennedy, someone else would have. No, probably not, right? Probably he would have died from cancer in the 1980s or something like that, right? So we don't accept it. So whatever the answer is to my question, right, under which conditions should we accept the conditional, the answer must be different for indicative conditionals than from subjunctive conditionals, right? In whatever way one makes the Ramsey test more precise, it needs to be sensitive to the grammatical mood of conditionals, right? And this is exactly what happened in the later literature. So when then people made the Ramsey test more precise, the answer was that the Ramsey test for the indicative conditionals is different and is made precise in a different way than the Ramsey test for subjunctive conditionals. I'm going to focus now on indicative conditionals, okay? But there is also a version for subjunctive conditionals, and it also uses mathematical methods, Okay. Now, the way to make the Ramsey test for indicative conditionals more precise, and that's also something that Ernest Adams suggested famously, is by means of subjective probability theory. Okay, subjective degrees of belief, as it were. So something looking like this here. So this diagram that you now see really depicts a little probability measure. And the idea is this, right? If you look at the little areas here, right, they all represent, as it were, possible worlds. Okay, so think of it in a way, there are three propositions, A, B, and C. Okay, A might be, you know, the weather will be nice tomorrow in Santiago de Chile, right? B might be the weather will be nice tomorrow in Salzburg in Austria. That's where I come from. I'm an Austrian. And C might be the weather will be nice tomorrow in Munich, right? That's where I'm a professor. Okay, and then, for example, this possible world here would be one where the weather will be nice tomorrow in Santiago and in Salzburg and also in Munich, right? All of them together. Whereas this area here is an area, a possible world where the weather will be nice tomorrow in Santiago de Chile, but not in Salzburg because it's outside of that area, right? And not in Munich, okay? And outside here, that's an area, that's a possible world where the weather won't be nice in any of the three cities. So you get the idea, right? So these are different possible worlds. And what the numbers depict are degrees of belief, sort of how firmly we believe, if this is my degree of belief function, how firmly I believe that this will be the actual world, okay? So you can see I put a lot of probability to this world here, right? Which is the world where the weather will be nice in Santiago de Chile, but not in Salzburg and not in Munich, okay? And it might be because I read the weather forecast for the three cities and that's what I found out, okay? And I find it completely unlikely, really impossible, as it were, right? That the weather will be nice in all of them, right? And so on. That's the idea. These numbers sum up to 1 to 100%, if you like. And that's, you know, a typical representation of a degree of belief function, okay? If you are sort of a rational agent, right? So, you know, a proposition like B, you would get the degree of belief by adding up the numbers for B. So the number here, 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 and here. And if you sum them up, you get the degree of belief. So, you know, if this is my degree of belief function, I find it quite likely that B is the case, that the weather will be nice tomorrow in Salzburg, for example, right? And the probability of not B would be the remaining ones, right? Okay. And this is part of sort of the coherence of the degree of belief function, which is sort of, which makes it a degree of belief function of a rational agent, okay? And now, probability theorists define what's called a conditional probability, okay? And the idea is, if you take that probability measure up here, the P, you can conditionalize it, as probability theorists would say, on that proposition here, for example, on C. And the idea is, sort of you assume or you suppose or you learn that C is the case. For me, the interesting thing is we can suppose that C is the case, okay? Because we're interested in conditionals. So let's suppose C is the case. How should, under that supposition, my degrees of belief change? And the idea will be, once I've assumed that C is the case, right, I can rule out all the non-C cases. That's why I have lots of zeros outside of C here, okay? The remaining numbers that were in here, they would not sum up to 1 anymore, but we need that in order to be coherent. So we multiply them, all four numbers with the same number, so that after this multiplication, we get numbers that would sum up to 1. And there is a unique way of doing it, and that will be conditionalization. So that's my degree of belief distribution, my probability measure after I've supposed C, right? So for example, the probability of B on the supposition of C, that is the conditional probability of B given C, right, is now 0.003, okay? Because if you sum up these numbers here, you see it's only just this little number. And the reason was, originally, I thought it was pretty likely that this is the actual world here, right, which was a B world, a way the world might be where B is the case. But on the supposition of C, this drops out, right? And so the remaining B numbers on the supposition of C, that's really just this little number here, okay? So first I thought it's very likely that B is the case, but then on the supposition of C, I think it's really, really unlikely that B is the case, and that can happen, okay? So that's the machinery that we are going to use. And now we can make the Ramsey test more precise in the following way, and that's been suggested by Ernest Adams, right, in the late 1960s and early 1970s. And the idea is, I measure my degree of acceptability for the conditional if A then B by the conditional probability of B given A, right? So I use the antecedent as something that I suppose to be true, like we did on the previous slide with C. Here it's A. And on that supposition, I determine my degree of belief in B, okay, like in the Ramsey test, okay? And then I use that degree of belief that I compute here, sort of outside the thought experiment, outside of the suppositional reasoning, to determine my degree of acceptability for the conditional, okay? So it's now no longer that we accept the conditional or not, but rather we give the conditional the degree of acceptability that's given by a conditional probability. I hope that's clear enough, okay? So what happened here is that when Ramsey was talking about knowledge, we really look at belief and we analyze belief as subjective probability, as quantitative degrees of belief, okay? And you can justify that on independent grounds. And then we understand the indicative mood of the if-then as a matter-of-fact supposition. So really we say to ourselves, let's suppose A is the case, right? Not let's suppose A had been the case. That's subjunctive supposition, but we mean a matter-of-fact supposition. Let's assume that A is the case in the indicative mood, okay? And a good formalization of that is conditionalization, okay? And then what happens is the acceptability of conditionals will be tied to conditional probability. So that's our way of making the Ramsey test now more precise, okay? And that's a very good idea, generally. Now, let's add another assumption, okay? So let's additionally assume that indicative conditionals are true or false at worlds, okay? Just like A and B were true and false at certain regions before. And now the idea is, well, indicative conditionals, if A then B, they are just like A and B. They are true in the one region and false in another and so on, okay? So for example, if a conditional is a material conditional, like we teach it to our students and we learn it in our lectures on propositional logic, right? If a conditional is a material conditional, it's just like the A and B. It's true and false at certain worlds, okay? Here we leave open whether the indicative conditional is a material one or not, but let's assume for the moment it's at least true or false. It expresses a proposition, right? It's truth conditional, that's the idea. But if that is so, then the degree of acceptability of an indicative conditional should simply be equal to the degree of belief to the subjective probability that we give to the conditional being true. Like we did with A and B, right? So how strongly did we accept A before? Well, let's compute the subjective probability of A. How strongly should we accept a conditional if it's like A and B, right? Something that's true or false? Well, we should measure it by its subjective probability, okay? So this idea gives us that the degree of acceptability should simply be the probability of the conditional, right? So on the previous slide, we had the acceptance degree should be a conditional probability. And now we've just said the acceptance degree should also be the probability of if A then B as a proposition. And if you put the two together, what we get is that the conditional probability would have to be equal to the probability of if A then B, where this is now, something that is true in some worlds and false in others, okay? And this is called Stolmaker's thesis, okay? Because Robert Stolmaker, famous logician and philosopher, has brought that up, this equality, for the first time in the 1970s, okay? And now here's the fact, okay? A little later, David Lewis showed in what's called the triviality theorem or an impossibility theorem that you can't have that. At least you can't have that generally, right? The only way to have it is for very trivial probability measures. But if you wanted to have that for arbitrary degree of belief functions, it wouldn't work, okay? And again, this is not a fictional story, but Robert Stolmaker actually proposed this equality here, okay? And then Lewis came along and showed you can't have that, okay? And this was a big surprise. So people didn't see that at all before Lewis proved his triviality theorem, okay? In the words of Dorothy Edgington, who is one of the famous contributors to this area in which we study degrees of acceptability of indicative conditionals, in Edgington words, this was the bombshell, right? So it had a big impact on the field, okay? And I won't give you the proof now why this wouldn't work, but it's basically you use probability theory to show that it doesn't work, right? And roughly speaking, what would happen is if Stolmaker's thesis were the case, right, then the probability of a conditional if B then C would have to be simply the probability of the consequent of C, which is of course absurd, right? In general, this is not the case, right? So, this can't be. Stolmaker's thesis must be false, okay? And you can really show that by mathematical proof. And now the question is, what's the philosophical message of all of that? Well, now this is now up to debate, right? We just have seen there's a certain combination of theses that we can't have. The combination was essentially, right, the suppositional theory of conditionals, that is the Ramsey test, okay, and the idea that conditionals are truth conditional, that they are true or false at worlds, right? If you put the two together, you get the impossibility. So one of them needs to go, and one way of addressing the problem would be to give up the thesis that indicative conditionals are true or false. But rather, we can give them degrees of acceptability, which are conditional probabilities, but they themselves, the conditionals, are not true or false at worlds. They're not like the A or B, right? They work differently. And then we're on our way of developing a theory of conditionals like Ernest Adams did, Dorothy Edgington did, and others, right? But you might also think, well, no, there's a more complex answer that solves that problem. Maybe indicatives are not true in a world, but true in a world and a context, right? And that's why we don't run into the impossibility result, and so on and so forth, and right? In any case, what happens then is philosophical progress is made, and that's exactly what happened in that area in the philosophy of language, okay? And now my point is, it wouldn't have been possible to find out about that without mathematization, right? You would just thought, yeah, well, why not combine the suppositional theory of conditionals, that's this one, roughly speaking, and maybe you wouldn't even have made it precise, with the idea that indicative conditionals are true or false, and then you would have gone on and developed your theory, but actually, you know, you can't because this is inconsistent, but you wouldn't have seen it without using mathematics, okay? And that's exactly what happened in the mainstream philosophy of language for conditionals. So if you read, for example, Jonathan Bennett's standard textbook on conditionals, you will find sort of everything that I've just described worked out in detail. And then there's a lot of discussion on the philosophical conclusions that we can draw from that, okay? So this is Ernest Adams, this is David Lewis, and this is Dorothy Edgington, okay? These two are no longer amongst us, so they passed away, but Dorothy Edgington is still very much alive and kicking, okay? And these are some references. Martin, I will send you the slides afterwards, and if you want, you can distribute them to the audience, so they might look up some of the references later if they want to, okay? So this was my first case study. Let me now move on to my second case study. That's a different area now. You might think of it as being a part of metaphysics, okay? And it's to do with similarity and ultimately with points in time, temporal points, okay? And the background is something that we know since Frege and Whitehead and Russell, namely definition by logical abstraction. And what I mean by that is, in some cases, in philosophy, but also in mathematics, but also in science, but even, you know, in commonsensical context, we are facing something that we call an equivalence relation, right? So, for example, we might look at the relation of a person having the same birthday as another person, okay? And then this is an equivalence relation because every person has the same birthday as the person, him or herself, right? And it's symmetric, right? If A has the same birthday as B, then also B has the same birthday as A. And it's transitive. If A has the same birthday as B and B has the same birthday as C, then A has the same birthday as C, right? So it's an equivalence relation. And then what Frege and Whitehead and Russell showed was there's a method of abstracting out from the equivalence relation the equivalence classes, okay? So in this case of having the same birthday as, the equivalence classes would be the sets of people that all share the same birthday. So there will be an equivalence class of people that were born on the 1st of January. There will be a second disjoint equivalence class of people that were born on the 2nd of January, right? And so on. So there are 365 equivalence classes for a normal year, right? And they do not overlap, and every person falls within at least one of these equivalence classes. And, you know, this step from equivalence relations to equivalence classes is an important one in lots of areas. Now, early on, and now I'm talking about the 1910s, 1920s, people like Russell and Carnap, who was mentioned before, and many others wanted to generalize this to the case of similarity relations, which are, you know, something like equivalence relations. They are also reflexive and symmetric, but they are not necessarily transitive, okay? And that's something that happens very often in the empirical domain, right? There, very often you're dealing with relations that are not transitive. Okay, I'll give you an example in a sec. But you still would like to abstract out, you know, something like equivalence classes, sort of generalized equivalence classes. Let's call them similarity classes, okay? So let me make that a bit more precise to see what I'm talking about. So nowadays, we would call a similarity structure essentially a reflexive and symmetric relation, okay? The relation might be transitive or it might be non-transitive. We leave that open, okay? And if things stand in that relation, we call these things similar in that sense, okay? So for example, take the points in the color space as the psychologists would study, okay? Colors, right? So the points encode, you know, brightness and you know, all the other parameters that you need for colors, okay? And then you could have a similarity relation that measures how close by color points are in the color space, right? And then these points would encode similar colors, so maybe different shades of red or something like that, right? And then you could have 2 points, they are similar, and this point might be similar to another one, and so on. But it can happen that the first point is no longer similar to the last one in such a chain, because the little differences might add up to become too big to still count sort of the beginning point and the end point similar. Right? That's why transitivity might fail, and in this case would fail for metric similarity, where similarity is given by things being close to each other, right? Now, what we want to abstract out is sometimes called these days a property structure, okay? So for example, equivalence classes would be properties, if you like, something that applies to certain objects, okay? By a property structure here, I'm just mean a class of subsets of our color points or human beings or whatever objects we're interested in. The empty set, let's not count as a property for simplicity, and let's assume every individual, right, every color point, every human being, whatever, has at least one property that applies to it. Okay, that's what I mean by a property structure. So, for example, in color space, color regions, like the set of all points that are red, right? The set of all points that are green and so on. These would be properties. And if you collect all these properties together, you get a property structure. That's the idea. Okay? And color regions can overlap, right? They do not need to be disjoint and so on. So they do not necessarily have to be equivalence classes. But if you took the equivalence classes that I were talking of before, they would also form a property structure in that sense. So a property structure is something quite general. Okay? And now, an old question in metaphysics is, and it's been around for a long time, what is prior, similarity or properties? Okay, and you find different answers throughout centuries, okay, in ancient philosophy, in medieval philosophy, up to this day, okay? Now we can study that in the following way by using our mathematical way of thinking of the problem. So one way of thinking about it is we have a property structure and we determine a similarity structure from the property structure. Okay? So here we would take a property structure to be prior to the similarity structure. Properties determine similarities. That's an old idea that you find in Leibniz. In a letter, he said, Peter is similar to Paul, reduces to Peter is A now, that is, has property A now, and Paul has property A now, right? So this is a reduction of similarity to properties. And if you make that a bit more precise, this idea, you can say that a similarity structure is determined by a property structure in the following way. You count 2 objects as similar, just in case they share at least one of these properties in the property structure. Okay, so that's at least one way of determining similarity from properties, and that's this Leibniz way here, right? So sort of identity would be objects share every property, right? And similarity would mean they share at least one property. It could also be 2 or 3, right? But if they share at least one property, let's count them as similar. Okay? Now we can also go into the other direction. So we can maybe start with a similarity structure and try to determine the property structure from similarity, right? Then we take similarity to be prior to properties. That's another point of view, right? How would we do that? Well, basically, we would form what's called the maximal cliques in our similarity structure. So a clique is a set of objects like color points or human beings or so, such that every 2 members of the clique are similar to each other, right? The idea is roughly, say you see some things are pairwise similar to each other, right? And really the reason is because these are all points that belong to the color red, as it were, right? So that's why they're all pairwise similar, because really they are all red points, right? How would you then get sort of redness out of the similarity? Well, you take together all the points that are pairwise similar, and you hope in this way you get red as a property, you get green as a property, and you throw in as many points as possible so that the clique property is still preserved, so you look at maximal cliques, okay? So you start by similarity and you determine the maximal cliques, and you hope thereby to determine the property structure from similarity. At least that's one proposal, right? If you don't like it, we can change it and study what happens then. But these are proposals that you find in the literature, and that's actually what, for example, Russell and Carnap suggested in their work from the 1910s and 1920s, okay? Now, if you, for example, start with an equivalence relation here and you determine the property structure in this way, what you get out is the set of equivalence clauses, right? So what we are now presenting is a generalization of the old idea that we started from, okay? Now, all of this is mathematically precise, but what we do is we just make precise what some philosophers have suggested maybe in an informal way, like Leibniz here, right? And this is important to note, this is mathematically precise, but there are no numbers, right? Nothing is to do here with numbers. The reason I stress that is because some people still have in their mind, maybe from school days or so, that when you do mathematics, it's always about numbers, right? But many philosophical problems are not involving numbers. So you might think, well, then I can't apply mathematics to them, right? But that's not true, right? You can have something that's purely qualitative, or it's about an ordering or something, no numbers involved, but it's still mathematical, and you can use mathematical methods to gain philosophical insights, okay? Now here's an example, right? See, here we have 4 objects, and now I've determined properties, and this is just, I take that as given, okay? So this is a property structure. I won't tell you where it comes from. It's what it is, right? It could be 2 colors or something, doesn't matter, okay? And now we could determine similarities by the method that I've just presented, right? So for example, 1 and 2, they share a property, so they should be similar according to our method. And now we determine the similarity structure, and you can see they are similar, right? You get all these similarities from the properties, right? And now is something that we can do is we take this similarity structure and then determine the properties in the way that I suggested, right? And you can see this is a maximal clique because 1 is similar to 2 and 2 to 3 and 3 to 1, right? And 3 and 4 build a maximal clique, okay? And that's all the maximal cliques there are, right? 2, 3, and 4 is not a clique because 2 and 4 are not, similar and so on. So if you determine now the properties from similarity, you get to the original picture, okay? So we start by properties, we determine the similarity structure, we reconstruct, right, the property structure from the similarity structure, and everything works fine because we end where we started, okay? Now, what's important here, we can now sort of exemplify this method of going back and forth between properties and similarity by little toy models. And that's another nice thing about mathematics, it allows us the study of toy models, right? And that's very important, okay? Now, as it was observed early on, so already Carnap observed that, and then later Nelson Goodman and others, this method by Russell and Carnap does not always work, okay? And here's an example where it doesn't work, okay? Let's assume we start in this way. This is the property structure. So now we have 3 properties. There is also this little 1-2 property here, okay? And now let's determine the similarity structure, right? It will still look like this. And now we determine the property structure. We know what happens. It looks like this. But now we have lost the property that we started from. And the reason is this little 1-2 property is sort of swallowed up by the bigger 1-2-3 property. You see that? So that's why when we determine from properties similarity and then try to reconstruct the properties from that similarity structure, we sort of forget about one property. And that's a problem, right? What we construct, right? They were all properties originally, so the method is faithful, as it were, it's sound, but it's not full, it's not complete, because we miss one of the original properties, okay? So the method that Russell and Carnap suggested sometimes doesn't work. Here it doesn't work, okay? But there are also other problems. Let's assume this is the property structure. So we have 6 objects now, color points or human beings or whatever, and now we have these 3 properties. Now we determine the similarities, right? Looks like this. And now we determine the maximal cliques, so trying to get back our properties. And then we can see we get another property here that wasn't a property originally, right? We get sort of a property that we shouldn't get, right? So everything that we want to get that was there originally, we do get. The method is here full or complete, as it were, right? But the method is not sound or faithful because we construct a property from similarity that shouldn't be a property, that wasn't there originally. That's the other sort of problem that we can get, okay? So it's 2 kinds of problems, all right? Now here's a question. Let's assume similarity is determined by properties. Under which conditions can we reconstruct the properties from the similarity? Okay, so when does the Carnap and Russell method work? That's our question. When does their method of abstraction work so that it is full and faithful? No problems emerge. Okay, And that's not an easy question with an easy answer. And I want to say you need some mathematics to answer it, but there is an answer, okay? And the answer is given by a theorem in what is called hypergraph theory, which is sort of an extended version of graph theory, okay? And the answer is, roughly speaking, you can prove that the method, as it were, is faithful, okay? Just in case the property structure looks like this, for every 3 properties, A, B, and C, there is a property X in your property structure that glues together A, B, and C. That is, that covers sort of their intersections, the intersection of A and B, the intersection of A and C, and the intersection of B and C. If and only if the property structure is closed under that kind of operation that I describe here, the method will be faithful. That is, what the method of abstraction will construct will at least be a property in the original sense, okay? Now, what about fullness, about not forgetting a property? Well, there's a necessary condition for fullness, namely that there is no property that is sort of a subset of another property. I mean, you might have noticed properties here are really extensional properties. So there are sets or classes, okay? That's a simple picture of properties, but in many cases, it's a useful picture. It's at least a good start, okay? So we already know if this situation is the case, then we can't get fullness, okay? And so this is trivial, right? This is not trivial. This is trivial. And what's also not trivial, if you put this necessary and sufficient condition for faithfulness together with this necessary condition for fullness here, you get what is a necessary and sufficient condition for faithfulness and fullness. That is, for Russell's and Carnap's method of abstraction being perfect, right? Reconstructing only things that were there originally, only properties that were there, and all of them, okay? So now we have an answer, right? So we can now check a property structure and know whether the method of abstraction that Carnap and Russell proposed works for that property structure or it does not, okay? And you can prove that in a mathematical way by induction over the numbers of objects here. Here the assumption is that we're dealing with finitely many color points or finitely many humans, okay? And when you use this criterion that we now get from hypergraph theory, you can show that the application that Carnap has of this method of abstraction in his famous book, The Logical Structure of the World from 1928, that actually the application of this method can fail there because these conditions are not always satisfied in the setting that Carnap has. But then again, the application of the method in Russell's book, Our Knowledge of the External World, which appeared a bit before Carnap, that works there because the conditions in the context that Russell uses the method for there, the condition is satisfied, okay? And you can always also prove that if properties originally are generated from similarity, right, then reconstruction of similarity from the properties will always work, okay? That's also something that you can prove mathematically, okay? So this is Russell here. I won't give you the details here, but in his application of the method, what he did was basically his objects were events, like physical events, right? Like a football game or something like that, okay? And the similarity relation was the relation of compresence of events. That is, 2 events occurring at the same time, okay? And then he wanted to generate properties, and his properties were temporal points, really. Okay, so sort of the property of an event occurring at a particular point of time. These were his properties, okay? And then basically I give the details here and you can look at them at home. Again, I sent you the slides later. But basically you can show that the method works because this condition that I've sketched in my theorem here are satisfied. And in order to prove that, you need the theorem that I've just given you and the theorem from convex geometry, because you need the geometrical structure of events and compresence to show that the method works fine in Russell's case. Okay, that's the message. And these are the references for that part. Okay, now let me wrap up by finishing with a little survey of methods, how mathematics is applied in philosophy today. So we all know mathematical methods are helping the scientists, right? When they try to describe and explain and predict natural phenomena. So this is well known. Think of physics, right? Or, think of economy, for example, right? But my point is that mathematical methods, and by that I mean also including logical methods, can also help us to philosophize in a better way. And this is because it can help us philosophize in a better way in the following manner. First of all, by improving the clarity and exactness of our philosophical concepts. Okay, so sometimes as philosophers we want to, define a philosophical concept. So, for example, Tarski famously defined truth. Okay, and then the logical and mathematical methods can help us by the definition of these philosophical concepts. So, for example, in order for Tarski to be able to define truth, and of course, as philosophers, we care about the truth concept very much, right? He used logical methods. He used higher order logic, or we would now use set theory, okay? But you need, for a Tarskian definition of truth, these logical mathematical methods, okay? Similarly, say you want to determine the degree of acceptability of a conditional, like in my first case study, right? You need mathematical methods to do that, right? So roughly, you want to define the acceptability degree of conditionals, and you use probabilistic methods, probability theory, to do that, right? Philosophers of science today, when they define scientific confirmation of a hypothesis by data, right? They make that precise. They define this confirmation relation in probabilistic terms. So again, in the definitions here of the definition, they would use mathematical concepts, namely probabilistic concepts, and so on. So that's one way of using mathematical methods in philosophy. Another way where mathematics can help us is by systematizing and justifying philosophical theses. Okay, so think of it in the way we want to justify a philosophical conclusion, a thesis. We want to argue for it. We do that all the time, right? Your usual philosophy paper includes some arguments, right? And then mathematics can help us in the following way. So we state some philosophical axioms, right? The premises. We add maths to the axioms, and then from that package we derive the conclusion. Okay, so that's pretty much also how mathematics is used by physicists, right? They have some physical law hypothesis and some experimental data, observational data. They add mathematics, and then they draw some conclusion, which might be a prediction, for example. And we can do pretty much the same thing, okay, in philosophy. So, for example, say your thesis is that if you're rational, your degrees of belief ought to conform to the axioms of probability, something that I used before in my first case study, right? Say you want to justify that claim, right? You need to justify that. Then you can do that by some philosophical assumptions and mathematics, okay? And, in the literature, these are the so-called Dutch book arguments, or decision theoretic representation theorems, or epistemic decision theory. You want to minimize sort of failures in accuracy, okay? But all of these arguments for these theses here, for this epistemological thesis, right, they use mathematical methods. So that's the second way in which we can use math in philosophy. The third way is we sometimes add mathematics to some philosophical assumptions or axioms, and then we prove not a philosophical thesis that we want to justify, but we prove a contradiction. Okay, and that's what Lewis did in my case study, my first one, when he had this impossibility theorem, right? So what this shows then is that basically the philosophical axioms that we were accumulating in the premises here, they are inconsistent with each other. But sometimes we can only show this inconsistency if we have enough mathematics available, okay? And what's the philosophical message then? Well, that not all of these philosophical axioms can be true, right? So some of them needs to be given up. Now the question is, should we give up the one axiom or should we give up the other? But in any way, this will lead to philosophical progress again, and that's the goal, right? So that's the third way of applying mathematics in philosophy, right? A fourth one is sometimes we can prove the consistency of a philosophical thesis or a philosophical theory by building a model in the sense of model theory, so in the sense of logicians, right? So for example, again, this is about truth, but not Tarskian truth. Say you want to have a theory of truth for a language, but the truth predicates should also be part of the language for which we want to have the theory of truth, which means we can have sentences that talk about their own truth and falsity. And, this should ring a bell. This sounds a lot like the famous liar paradox that already was studied by the ancient Greek, right? Like a sentence that says about itself, I'm not true. And then you assume it's true, and it seems that it must be false, but you assume it's false, then it seems it must be true. So there's a problem here, right? But as Saul Kripke and Hartwig Field and many others have showed, that if you change some things, right? So for example, you give up classical logic and you turn to a non-classical logic, you can have a theory of truth for a language where the language includes that very truth predicate, right? And then maybe the liar sentence, right, might have the third truth value or something else, okay? But now basically you need to show that this is not just a proposal, but that it's consistent at the very least. You still need to argue that it's a good philosophical theory of truth, right? But at the very least, you need to show that it's consistent. And they did that by building a model, and the model is a mathematical model, right? So, and that's, of course, one of the virtues that a philosophical theory or a philosophical thesis should have. It should be consistent. And you can prove that by mathematics, okay? And the final way of using mathematical methods in philosophy is sometimes you can argue for the plausibility of a thesis, okay, by looking at toy models. And now these are models not in the logician sense, but in the sense of physicists, right? So something like an idealized system. Remember my little graphs, similarity graphs and property structures that I had in my second case study, right? With the 4 objects and the 6 objects. These were toy models, right? And there we were finding what kind of problems abstraction methods could have, right? And that's also very important. That's also something that we are enabled to look at by mathematical methods, okay? So for example, Kevin Solman has a nice paper where he studies the epistemic benefits or shortcomings of special kinds of diversity in science. So is it good to have a diverse scientific community? Is that good for science or not? And he studies that in the paper, so it's a philosophy of science paper, okay? But he studies it in terms of toy models, okay? And he studies these toy models by means of computer simulations. And that's not weird, but it's something that's happening all the time, for example, in formal epistemology these days, okay? So for example, if you take the master program in Munich at the MCMP, where I'm working, we also teach our students how to use computer simulations when they want to write a paper in formal epistemology, okay? But you can only use toy models and computer simulations once you have mathematics, okay, applied in your philosophical theory. So that's the final way, I think, in which we can use mathematics in philosophy, okay? So here are some references. And, you know, if you want to look at the slides at home, I mentioned here lots of other examples, okay? So the black thing is, right, the philosophical topic or area like philosophy of time. And in blue, you can always have a look at the mathematical methods that are used to study that philosophical area. In this case, it would be temporal logic, for example, right? And, you know, the same for other things, okay? So have a look at these examples, right? So for example, in the philosophy of mathematics, we would use the incompleteness theorems, right? Gödel's incompleteness theorems and so on, okay? But have a look at these examples yourself, okay? Now, where I'm working, that's the Munich Center for Mathematical Philosophy. And what my colleagues and I have in common is not the area in which we're working. We're working in all sorts of philosophical areas, okay? But what we have in common is really that we use sort of mathematics as a kind of lingua franca, right? So we all talk mathematics while addressing our philosophical problem, okay? So if you're interested in that, have a look at our website, okay? And I should mention there's also something called the Summer School for Widening Participation in Mathematical Philosophy that happens annually in the summer, and it brings together students who want to learn about mathematical philosophy, okay? And the Summer School is especially there for students you know, who might not study at, you know, already at an institute that uses a lot of mathematical philosophy, right? It's especially a summer school for underrepresented minorities in philosophy and so on. And maybe for some of you, it might be interesting in the future, okay? Now, what we found is, I hope, that mathematics is required to show that a theory of conditionals cannot be suppositional and truth conditional at the same time. This was my first case study. Maths was a necessity there, okay? And secondly, mathematics was required to determine the conditions under which properties can be reconstructed from similarity. And again, you needed mathematics to determine these conditions. And more generally, mathematical methods can play a similarly important role for philosophy as they can do for science. And this, I hope you could see a glimpse of when I gave this little survey of methods in philosophy. And again, at home, have a look at my numerous examples that I'm giving, okay? So let me conclude with a quote by Leibniz, who was suggesting that, precisely that, for the future of philosophy when he said, the only way to rectify our reasonings, like philosophical reasonings, is to make them as tangible as those of the mathematicians, so that we can find our error at a glance. And when there are disputes among persons, like two different philosophers, we can simply say, let's calculate, let's calculemus, and then let's see who is right, okay? Thank you very much.
Excellent. A very truly insightful talk, Professor Leitgieb.
Thanks so much, Martin.
You can see the claps in in the chat. So
Thank you.
I think after we congratulate Professor Leitgieb on this talk, it's time for questions. We have, I don't know if you have time. We have time.
Absolutely, of course.
Beautiful. So if you feel free to raise your hand, and if you want to speak, you can do that. And here we have a question from Eric Pessoa. Thank you for the talk. Very interesting. I understand the application of pure mathematics, proof-related disciplines like logic, model theory, probability theory, to philosophical problems. For example, after formalization, finds inconsistency. However, I'm curious if you think theories from applied math can be used in philosophy, dynamical system theory, optimization theory, or do you think the conceptual nature of philosophy demands the need of abstract mathematical theories? Good question.
That's a good question. Yeah. So yes, I think that it's sort of easier most of the time to apply methods from pure mathematics in philosophy for precisely that reason, right? You see, purity was already occurring in my Kant quote very early on in my talk, right? And you might think there's a reason why pure maths and sort of the pure concepts that Kant was mentioning about philosophy, that there is purity in both of them, okay? But, you know, this doesn't mean that methods from applied maths are completely out. We just might have to work a bit harder to make them applicable, right? So with all of that, we always need to make mathematical methods applicable in philosophy. And that process in itself needs sometimes some ingenuity, right? So that already is sophisticated and problematic, and sometimes people lack a handle. Then someone comes along, maybe some of you in the future, right, and find a way of making maths applicable, right? We need to work hard, okay? But this doesn't mean it's impossible for applied math. So let me give you an example, right? In the philosophy of science and also in metaphysics, we are very much interested in laws, right? Natural laws. What are laws, right? You know, in physics, right, what's underlying laws typically is dynamical systems, of course, right? Discrete dynamical systems, but also continuous dynamical systems, systems of differential equations, right? So, you know, from that point of view, right, a philosopher who is interested in laws better knows about dynamical systems, right? And then it could be, if you're a philosopher of science and you want to, you know, philosophically reflect on laws, okay, sort of in the applied sciences, right? Then in your philosophical theory of these laws, you really need to talk about, you know, dynamical systems as they come up in applied mathematics. And it might be that then methods of applied mathematics will pay off for you, okay, as a philosopher of science who wants to study laws, for example, okay? Another place where this could come up, that's something that I've been interested in. So I did some work on logical descriptions of artificial neural networks. So the idea is, right, you have an artificial neural network, and that's essentially a dynamical system, right? A neural network has some states, and you give it some input, right? And then, you know, the input changes the state of the network, and, you know, afterwards the network changes again. Maybe it finds an equilibrium state that's sort of the answer of the network, and so on. It's a dynamical system, right? Typical here at this discrete dynamical system. And then what I did, and some other people did and were interested in, was, can we describe this dynamics of the neural network in qualitative logical terms? For example, in terms of conditionals. And the answer is yes. And, you know, if you were interested in that, I could tell you more. But there, in order to show that this is possible, I and my colleagues, we needed to look at dynamical systems theory. Otherwise, we wouldn't have been able to prove our soundness and completeness results of our logic of conditionals with respect to what we call a network semantics, okay? So these are two examples where I think dynamical systems and methods of applied mathematics can actually help us, but we just need to work a bit harder.
Excellent. Eric, if you want to make a follow-up, otherwise we can move on. But in that case, would be a philosophical interpretation of dynamical system instead of the application of dynamical systems to philosophy?
That's right, but the philosophical theory, because it's to do with dynamical systems, will also have to invoke methods of dynamical systems. That's the point.
Yes, yes, that's very good answer, Professor. So, so Joaquin, if you want, you're free to speak.
Thank you a lot. Well, I want to start by thanking you, Professor Leitgeb. It was a wonderful talk. I enjoyed it a lot.
Thank you.
And I find this topic and methodology to be extremely useful and a great step forward in philosophy. My question is about what I would call some edge cases in which the applicability of philosophical methods to or mathematical methods to philosophy seems to be at least not as not as clear of regarding the viability of applying such methods. I'm thinking, for example,
Yes.
if we have a philosophical discussion on the on which mathematical system, if any, is the one that structures reality, or that truly reflects the relations of our ontology, for example. Then to apply some sort of mathematical model to reason on that topic would, to me at least, seem to be bordering on question begging, because that precisely is what we're discussing. If such methods reflect not or don't reflect reality, so if such mathematical structures, what would you say on those edge cases? Do you think there's still a way to incorporate this methodological point of view of mathematics applied to philosophy, or do you think that those cases are ones in which we have to, at least for the time being, leave mathematics out of the picture?
So let me try to see whether I understand your question. So if you're interested in sort of, to describe the structure of the empirical world by the use of mathematics, right? Then this is okay for you, right? This is not a problem. Is the question really, we couldn't sort of justify mathematics by applying mathematics again, because then we would run in a circle? Is that the question?
Yes, but more specifically in cases in which the applicability of mathematics or the correct mathematical system that reflects the structure of reality is precisely that which we are discussing.
But what do you mean by reality here? So do you mean the empirical reality or philosophical, sort of the reality of philosophy, or mathematical reality? What's the reality here?
Well, I'm thinking more about discussions in maybe in metaphysics, I would say.
In metaphysics, good. But then what's the metaphysics of? So for example, you could be interested, very often metaphysicians are interested in metaphysics of the empirical world, metaphysics of science, right? But you could also be interested in the metaphysics of abstract entities, right? Including, you could be interested in the metaphysics of mathematics. So my question is, again, metaphysics of what? And then I'll try to answer your question, okay?
Well, let's say I'm interested in metaphysics of mathematics.
Okay, good. That's what I thought, right? So there, the worry might be, right? We are, say, interested in the metaphysics of mathematics, right? What are these mathematical objects, right? Numbers and functions and sets, right? And are truths about them necessarily true, right? So these are all questions that we might be interested in metaphysics of mathematics, right? And then your worry might be, if we are using mathematical methods to do metaphysics of mathematics, this would be sort of circular question begging, because on the one hand we want to study the metaphysics of mathematics, but then we use sort of the same methods studying them, and then we run in the circle. That's what you're worried about, right?
Yes, precisely.
Good, excellent. Okay, so that's a very good question. Now, to some extent, I think, in philosophy, we need to live with these kinds of circularities anyway. Okay, so this is a typical feature of our field, and you might notice that when you give a logic course, for example, right? Or remember when you had a logic course back then, okay? So, you explain, for example, you do propositional logic, and you explain the semantic rules to the students, right? Where you explain the truth conditions for conjunctions and formulas, and disjunctions or formulas, and negation formulas, and so on, right? And then what happens is you say, right, you know, a conjunction formula, the conjunction of A and B is true, just in case A is true and B is true, right? And then if you have clever students, someone will raise the arm and say, but look, haven't you just explained the and with another and here? Right? Because there's the and in the conjunction, and there's the and in sort of when you explain under which conditions the conjunction is true. So aren't we running in a circle? Right? That's a very similar kind of worry. And the answer is yes and no, right? In some sense, there is a circle, but it's not a vicious circle, right? And the reason is, in terms of languages, right? One is the conjunction in the object language, and the other one is the and in the meta language, right? And the meta language, that is typically, you know, in my case, it would be German, right? Or for all of us, English, right? Or in your case, you know, Spanish, right? Or whatever. But it's something that we take already as given, and we take, it's highly imperfect, but sort of we have some kind of understanding. We can use natural language, right? And then we use it, plus a little bit of maths and so on, to get a better handle on conjunction and disjunction in the object language, right? And we show, you know, a soundness result for propositional logic and a completeness result. So this is something that we couldn't have done without going through the Logic 1 course, okay? And then ultimately after the course, what happens is, I think, right, that sort of there's a kind of feedback effect that we also then start to use and or and not in natural language in a clearer and more precise and more systematic and more consistent manner. Okay, so you have not just gain some philosophical insight into the object language, but also into the meta language, which is natural language. Okay, and I think something like this will be going on also in the case that you are describing, right? So what would happen is we would use math as a method, right? As something, you know, as a kind of extended form of logic that we can work with, that we have been trained with, that we have some rough and ready understanding. Okay, and then we build our philosophical theory, in this case, a metaphysical theory of some mathematical entities, some mathematical ontologies, some mathematical concepts, and so on. Okay, and we would use these mathematical methods, even though they might also be sort of in the subject itself. Okay, but you know, it's not different on a different language level, so it's not a vicious circle that we're running into. Okay, and then if we build a good theory and get some insights, then, if things go well, there will also be a feedback effect on the mathematical methods that we use to do metaphysics here. And I think actually that happens. Okay? For example, right, if you're a logicist about mathematics, then you think mathematics can be reduced to logic, right? That's what Frege thought, and Russell and Whitehead, and you know, in more recent days, Bob Hale and Crispin Wright, neologicism, and so on, right? But a neologicist and a logicist back then, you need to have some higher order logic, right? You need second order logic, you need a type theory, something like that. And then, if you're lucky, you build a good logicist theory and show that in one way or the other, you can reduce mathematics to logic, right? But you needed to have a starting point, and this was higher order logic, right? And higher order logic already includes a bit of math, otherwise this reduction wouldn't work. Okay, but you sort of take it as a given, and we have a good understanding and sufficient understanding. That's why we can start with it. But once we understand mathematics as a branch of logic, in a sense, I also think that we get a better understanding of logic itself, that it already includes mathematical structure, and we have learned something about our starting point, namely higher order logic. Okay, so I think that's what happens in these borderline cases that you were describing. Does that help?
Yes. Thank you a lot. That was really great answer.
Very good question. Thank you. Thank you.
Thanks, Joaquin. We have one more question by Gaby Donoso. Thanks you very much for the great presentation, Professor. My question is the following, and I hope the conjunction I intend to put to you is understood. Do you see a virtuous compatibility between your projects of mathematical philosophy and the program of naturalized metaphysics, of authors like Lehmann and Ross, or Chakrabarty's scientific ontology? I mention this because I see many common theses with regards to discursive clarity and continuous philosophy with the sciences and their tools.
Excellent. Yes. So there is some continuity, and In fact, James Ladyman is a former colleague of mine and a friend of mine. So we, a couple of years ago, I was a professor at Bristol where there's James, and we wrote a paper on structuralism together. So yes, in these areas, logical and mathematical methods pay off, right? To give you an example, right? That's something that James is interested in, right? Ontic structural realism, right? So there's structural realism as something that's meant to be in between realism and anti-realism in the philosophy of science, right? So the idea is that even phlogiston theory back then got something right, namely, well, they got them sort of the ontology wrong, right? It's a false scientific theory, right, about combustion. We have a better theory now. But what they got right is they got something right about the structure of the world, as it were, right? And that's the idea that structural realists have, okay? So there is some continuity sort of in the development of science, but it's on a structural level. The old empirically successful theories and the current empirically successful theories, they have something in common, but on a structural level, okay? That's the idea. And what James's own brand of structural realism is an ontic structural realism, okay, not an epistemic one. So an epistemic structural realist would say the only thing that we can know about the world is what its structure is like, right? But I've just talked about knowledge, so it's an epistemic version, as it were, right? Whereas a ontic structural realist like James would say, well, no, the world itself is structural, like, and a typical example case would be quantum physics, right? Where you got entangled particles and you need to think of these particles as being part of a structure, right? Okay, so this is structural realism, no math so far, but here's the point. Now, a good philosophical question now is, what are these structures that ontic structural realists like James Ladyman are postulating, right? And here you can learn a lot from, philosophy of mathematics. In fact, there's a whole branch in philosophy of mathematics called structuralism about mathematics, okay? And what the structuralists about mathematics mean by structures resembles very much what structural realists in the philosophy of science mean by structures. So the one can learn a lot from the other. And structuralists in the philosophy of mathematics, they use logical and mathematical methods to try to make clear what a mathematical structure is. Again, for example, second order logic would be something that's typically used, okay? So if you're interested, I wrote 2 papers on a structuralist theory of unlabeled graphs, a branch of graph theory, where you want to think of these graphs as structures, right? So they have nodes and edges, right? But roughly speaking, if you have 2 nodes and an edge, and you permute the 2 nodes, you get the same structure again. Nothing changes. So permutations don't change anything, right? That would be an unlabeled graph, okay? Sort of the nodes only have an identity as being part of this graph, and that's all there is to it, okay? So these graphs are not sets, okay? But they're entities of their own kind, they're structures. And what I do in these 2 papers that I once published in Philosophia Mathematica, I gave an axiomatic theory of unlabeled graphs as structures in that sense, okay? So it's a kind of non-eliminative structuralism about unlabeled graphs that I developed there. And if you look at my paper, you can see that I use second order logic, and this is very important, okay? I use mathematical methods, I prove the consistency, I build a model for my formal theory and all of that, okay? And thereby, I think I give a good philosophical answer what structures are, namely, at least what unlabeled graphs are as structures. And now if you're a structural realist, right, because you want to naturalize metaphysics, okay, say the metaphysics of quantum physics, then I think you can learn a lot, I hope, from my paper and, from papers by other structuralists in the philosophy of mathematics. And you can use the mathematical methods that they use to get a better handle on your naturalized metaphysics of, quantum structures, okay? Let me conclude with one point here. You shouldn't think of it in a way that only if you're a naturalist in philosophy, mathematical philosophy will be interesting for you, okay? That's not the case. And I mentioned a person in my talk who would be a very good example case, namely Carnap, okay? So famously, Rudolf Carnap used logical and mathematical methods a lot in his philosophical work, right? From the beginning. So I mentioned the logical structure of the world, the Aufbau, right? That's to do with similarity, lots of logic and maths there, right? And then later, when he was doing philosophy of mathematics in the logical syntax of language, and when he was doing modal logic, right, in meaning a necessity, and when he was doing inductive logic, right, in his late work on probability theory and inductive logic, he used logic and mathematics everywhere. So he was a mathematical philosopher, right? But you wouldn't want to call him a naturalist, right? Because unlike a standard naturalist, Carnap did not think that philosophy is like science. For Carnap, science and philosophy are not sort of part of one big continuum, as it were, right? As a naturalist like Quine, for example, would think, okay? Or someone like James would argue, okay? For Carnap, philosophy was still different, right? It was sort of, as it were, the logic of science, right? It was to some extent on a meta level if science is on an object level, right? So, you know, he was not a naturalist about philosophy, okay? For example, his favorite method would be something called rational reconstruction or explication, okay? And he would use that within philosophy, but he didn't think thereby that he's doing science, okay? So there's more to be said about it. It's not relevant now, but this would be an example of a philosopher who is not in this naturalized camp that was mentioned, but he's still using logical and mathematical methods a lot, okay? So don't think mathematical philosophy is necessarily tied to naturalism. What it is tied to is sort of doing philosophies in a broad scientific spirit, doing philosophy in a way where you're happy with applying scientific methods, maybe because you think philosophy is just a science, that you're a naturalist, or maybe because you think philosophy is helped by the scientific methods, like Carnap, but you're not a naturalist. It doesn't matter. But you need to be sort of a scientifically minded philosopher to use mathematical methods. That's sort of the presupposition. But these days, many, many philosophers are sharing this sort of scientific spirit, okay? And that's why I think mathematical philosophy has become very popular.
Very good. Thanks, Gabi, for the question, and thanks, Professor, for the answer. And if there are no more questions, I would like to appropriate the microphone for a little bit. Well, first, Gabi, Professor Leitgeb has an article of a paper from 2013, if I remember correctly, where he makes a comparison between scientific philosophy, it's not naturalized metaphysics, of course, and mathematical philosophy. It's a very good article and can give you some insights about this work.
Thank you.
And for a sum up and closing up, I would like to ask you some more question in a personal note. First, it will be two questions. I make them both, and then you answer both. First, given your background in mathematics, what kind of what topics on mathematics should a philosophy student might study? I mean, of course, we have logic and probability theory, but else, I think, like topology or else. And finally, what areas of scientific and mathematical philosophy do you personally find the most exciting right now? And if you can thought about it, where do you see the field in the next 10 years or so? Or where will be people working in 10 years? That's it.
Good. Very good question. Yeah. So about the first one. So yes, you mentioned logic, right? That's been there for a long time, and I think it's still there for a good reason. And by that, of course, I mean, you know, propositional logic, first order logic, and modal logic, and a bit of higher order, second order logic, something like that. That would be great. Okay. A bit of probability theory. So, you know, you've seen that in my examples. And additionally, I would recommend a little bit of calculus, right? Real numbers, functions of real numbers. Okay. A little bit of discrete mathematics, where we're studying discrete structures. Graphs would be an example. Okay. And I would say that's pretty much it. Okay. And now, other than that, I would recommend, you know, if you find out that you need something more for some good philosophical reasons, then with the background that I've just described, you will be able to take your textbook out of the library or download it or get a course or so, and to make yourself familiar with the mathematical machinery that you need for the philosophical problem at hand that you want to deal with. Okay? Right? So but you don't need that sort of as in the basics. Okay? The basics, I think, would be a little bit of logic, a little bit of probability theory, a little bit of theory of real numbers, a little bit of discrete mathematics, and maybe, ideally, it would also be nice, a little bit of set theory, right? A little bit of foundational work. That would also be good, right? But other than that, you know, that's enough for the basics. And that's not so much. It might sound like a lot, but it's not, okay? It's perfectly doable for all of us, okay? Now, with respect to the other question, so I'm not sure I want to make any grand-sounding conjectures where the field is moving or so, but I can give you two examples, okay? One that I'm personally interested in, and the other one something that I'm also interested in, but that will be of general importance, I think, okay? The first one is something that I'm currently working on is a logic of reasons, okay? So reasons in the sense of the philosophical literature on reasons, and that's mostly literature in practical philosophy, right? Where moral reasons for actions, for example, right, are studied a lot, okay? And that's a big hype, or has been a big hype in the last couple of decades, okay? But also in epistemology where there are reasons for belief, epistemic reasons, right? I give you reasons and that has some kind of impact on belief, and these are normative reasons or explanatory reasons and so on, okay? And now, something annoying is the case from my point of view, right? There is this big philosophical literature on reasons, but typically it's not done in a formal method, in a formal way. Okay, this is not completely true. There are exceptions. So, for example, Jeff Horty has used default logic, that's a branch of non-monotonic reasoning, in order to make precise what reasons are and how they work, right? And others have used, you know, some other methods. So there is a little bit here and there, but there is not much. And this is almost a scandal because there is this big body of philosophical knowledge, right? But there's hardly any formalization thereof, okay? And I think this has two downsides. I think the philosophers who work on reasons, they would benefit a lot from the formal methods. I think there would just be better theories out there. And on the other hand, those who work formally, they do not make use of the insights that these philosophers have about reasons, right? So if you go to formal epistemology workshops, you will not find lots of talks about reasons because, you know, they have not been, you know, formalized, as it were, right? So there is a gap here. And something that I'm currently interested in is building a bridge between these two areas. So I've just written a long paper on the logic of epistemic reasons, where I give an axiomatic system for epistemic reasons, normative reasons for belief, right? And to give you a rough and ready idea, reasons end up being something like vectors, okay? So if I give you a reason, then basically I give you a vector, and a vector has a direction and sort of a length, right? And what it is, it's something like a push or a pull on your subjective probabilities, on your degrees of belief. Right? And if we exchange reasons or we put forward reasons when we argue, the way I want to describe that in my axiomatic theory is that we sort of present in one way or the other, maybe linguistically, vectors that are meant to push rational degrees of belief around. And when you have lots of reasons, how do you aggregate them? How do you put them together? Well, by summing up the vectors. So they are like forces in physics. When you have a couple of forces and you want to aggregate them, what do? Well, we sum them up, right? And then we need to have a philosophical story, and that's also part of my axiomatic system, what the effect of a reason is on our degrees of belief, on our subjective probabilities. We need something like, how can we update probabilities by reasons? And my axiomatic theory tells you how to do that if you're rational, okay? So I think, you know, in this way, I build this kind of bridge, and if it's successful, then, you know, in the future, you know, there might be a lot of cooperation between these two fields where there's not a lot of cooperation right now. And I don't think of my theory as sort of being the final answer, but rather, you know, hopefully this will get published and hopefully some of you will read it. And then they will see axiom number 3 and they will send me an email and say, Hannes, I like your theory, it looks great, but I don't think your axiom 3 is plausible at all. Okay, rather I want to replace it by axiom 3 prime, and then you change something, and now you defend your own theory. You build the bridge a bit differently. And then some other colleague comes along and says, no, and that's how it goes. And then we explore the space of possibilities here, and in all of that, we are making a lot of philosophical progress, okay? So that's a field that I think is underdeveloped, but it might have a lot of future, I think, okay? And the other part that I wanted to mention was, and there I'm not a specialist, but I'm interested, but it's something that we need urgently to work on. And if you have a look at my slides, I mention it very, very, very briefly at the end, okay? And this is philosophy of artificial intelligence, okay? So we all use, ChatGPT. We all use our large language models, right? We all use our huge artificial neural networks trained by, big data available in the World Wide Web, okay? And as the computer scientists themselves observed, right, these are just black boxes, right, which come up with good recommendations or with good predictions, but we lack methods to look into the black box, right? And that's a problem, as we all know, right? So, if you apply for a loan and the AI system will reject your application, right? It would be nice to be able to ask, what are the reasons for your decision, right? And if the AI system predicts that you will be a criminal in the future, right? It would be very nice to see the reasons for that, so that we can maybe, say these were not good reasons after all, right? But currently, right, these AI systems don't give us reasons, and we can't read the reasons of the system, right? So that's what people are interested in explainable AI. And I think philosophers using mathematical methods might be able to contribute to explainable AI, right? And I can sort of exemplify that with the theory that I've just mentioned, this axiomatic theory of reasons. I'm currently writing a paper on that with my colleague Levin Hornischer, who knows way more about neural networks than I do. And what we try to do is we use this philosophical theory, this axiomatic theory of reasons that I've just mentioned, and try to turn it into something that we can apply in order to sort of pull out the reasons for which a neural network comes to a decision or makes a prediction. And that would then be an application of a philosophical theory in explainable AI. And that, I think, will be very important, right? And if that doesn't work, maybe something else will work. I think philosophers should have a say there, okay? Because ultimately, the question is, can we justify what the AI system is doing? And that's the philosophical question. And the only way to answer that philosophical question, to address it, is by using mathematical methods, simply because the neural networks themselves are mathematical in nature, and simply because we want to implement our methods then in a computer. So it needs to be formalized, it needs to be computable, right? So that's, I think, where in the future mathematical philosophers could have a lot of very, very good society impact even, okay? But it's early days, and we are yet to see whether this will work and how this will work, if it works, but it's an important topic.
That's actually great, Professor. You talk about the logic of reasons, and that couldn't be better, because we have our reasons guy here in the HEFA, who is Cristobal. And he have a question for you, actually, about this talk.
Great, excellent.
Thanks you for the great talk, Professor. I would like to ask, what's your opinion on the possibility of applications of mathematical methods to practical matters? I'm deeply interested in ethics. Would you consider Rawlsian reflective equilibrium a mathematical method, as maybe could be interpreted in Charles Parsons' work, which was actually first thought as a decision procedure for ethics?
Yes, so very good question. Yes, I do think mathematical methods can have lots of fruitful applications in practical philosophy. I just mentioned one, right? Reasons for action. Then I think we want to make progress, and there we use mathematical methods. But of course, deontic logic, right? The logic of norms, that's still important, right? We want to be able to have a notion of a valid moral argument, but we can only have that when we do deontic logic, right? So this is very important. Decision theory, right? That's part of practical philosophy, and that's a form of theory, right? That involves, of course, probability theory and utilities. Consequentialism as a brand of ethics, right? It makes use of these methods. and so on and so forth. Okay, so in practical philosophy, formal methods are very important, right? For example, my colleague Christian List at LMU, he's using formal methods a lot in his work in practical philosophy, right? Think of theory of social choice, right? Uses, of course, lots of formal theory and so on and so forth. About reflective equilibrium, I don't think of reflective equilibrium as a formal method. It's an informal sort of philosophical method, as it were, right? But it can also be used in mathematical philosophy. That's the first thing, right? And you might want to use mathematical methods to make more precise what we mean by reflective equilibrium. Okay, so that's the two ways how reflective equilibrium relates to mathematical philosophy, right? So Charles Parsons would work in philosophy of mathematics, and sometimes you can argue for a thesis in philosophy of mathematics by a method of reflective equilibrium, right? Like Rawls had it in his theory of justice, right? But maybe, we are not happy enough with the current descriptions of what the method of reflective equilibrium is. And maybe we can even make that method a bit more precise, right? By using logical or mathematical methods. I don't think this has been done, but I don't see any principal reasons why it couldn't be done, okay? This is yet to be seen. Someone would have to try it, okay? And then this would be part of metaphilosophy, because we would then sort of, reflect philosophically on our philosophical methods, here the method of reflective equilibrium. And then maybe mathematical methods could help us, right? In other cases, this has been done. So for example, another philosophical method I mentioned before is Carnap's explication of concepts, right? Where you take a pre-theoretic concept, like truth as we have it in everyday language, and then we try to make it more exact, clearer, more systematic, more fruitful, okay? Like Tarski's explication of the pre-theoretic truth concept by his Tarskian definition of truth, right? That Carnap, this transition from the old to the new concept, he called an explication, okay? And that's in itself also, a philosophical method and not necessarily formal in itself. The output of an explication will involve formal methods, but the method might not be formal, right? But some philosophers recently have used formal method to make more precise what that transition is, okay? And a former PhD student of mine, Matteo De Benedetto, he wrote a paper on that, and he used formal methods. He used the theory of conceptual spaces by Peter Gardenfors to try sort of explication, as it were, okay? To make explication more precise, and he used some formal methods of doing that. And that might also be something that we in principle might be able to do when we look at reflective equilibrium.
Many thanks, Professor, again, and thanks, Cristobal, for the question. I think that he will be contacting you soon, Professor, and we will...
It will always be a pleasure. Absolutely.
Thanks. And we will all be expecting those papers you mentioned earlier. And well, I think there are no more questions, and I think that it's maybe time that we should let Professor Leitgieb go to bed. It's 1 a.m. actually. So, well, summing up, Professor, it was a pleasure. We thanks you all for participating, and thanks for the explicit response and exhaustive responses to all of our questions. In the name of ACHEFA, we are thrilled to have you here, and we expect to hear from you in another moment if we will invite you again sometime. Okay. So
thanks so much, Martin, for setting this up. Many thanks to all of you for attending and for your excellent questions. And, always feel free, obviously, to get in touch with me, right, by email or so. And otherwise, I hope to see you in the future, maybe in Munich, maybe, at some conference. Let's stay in touch, okay?
Yes, let's stay in touch. And we all have now to apply to the program of LMU.
Yes.
That would be it.
Okay.
Professor. Goodbye.
Thanks so much. Bye-bye. All the best.
All the best.
Bye.